Good day, I'm Dr. T and welcome to my office. So in this video, I want to start a short, maybe 4-part series about Earth systems, and our relationships with those. Now at the start of this kind of series, I do want to start out with a little bit of further reading and a couple of caveats. I'm a chemist, so I'm definitely coming at this from a chemist point of view. This will probably show the most in the last video where I'm discussing our relationship with Earth systems. But I will definitely have some influence in other videos as far as being a chemist. Also, I'm definitely going to use some further reading because in this video, it's going to be me as a chemist trying to tackle meteorology. I'm going to do my best, but this is only an intro. And if you want to dive deeper, I strongly encourage you to do so. A couple of resources. LibreText, always love these guys. Wonderful open source textbooks. And they do have a LibreText Practical Meteorology that I'm going to reference. And then there's the YouTuber Weatherbox. They are a meteorologist. I believe they definitely have studied meteorology, and they've done a wonderful, really introduction, very accessible description of meteorology. So if you want to dive a lot deeper, I'm strongly going to recommend Weatherbox content for you. They do an excellent job. Okay. So let's dive in, and to start Earth systems, let's kind of start from the outside and move our way a little bit in. It's not really the format I'm going to do, but I do want to start out with the atmosphere. And so here's Hello World, or one of a couple of images. This was taken by the Artemis II mission. Basically, they had a really nice camera, they pointed it out the window, and they started shooting. They got some good photos. There's a couple of time lapses. They're really kind of nice. In one of my other videos, I have one of their time lapses that was compiled by a Redditor. But in this one, this is just a still. And so, of course, kind of gives you a perspective of the world we live in. This is the night side. The Earth is illuminated by the moon because Artemis II took place during a full moon, which was kind of cool. But with this one, what I want to point out, because we are talking about the atmosphere, is, of course, the Earth is surrounded by atmosphere. We got a bunch of gas, and Earth's got a bunch of gravity, and the gravity pulls the gas in, and we get this layer of gas around us all being squished down with gravity. Now, that layer of gas, depends on how you want to define it, goes up pretty far, but most of the atmosphere is fairly close to the Earth. Gravity holds it in pretty good. You still got a few, stray atoms bumping around elsewhere, but the bulk of the atmosphere is actually fairly close to the Earth. And the reason I'm showing you Hello World, one of the things that when I saw it, like, you're kidding me, you can see that, is going to be this faint yellow line that goes around the Earth. It is just barely above the Earth. It looks almost like it's hugging it. Had the resolution been any less, you wouldn't see it at all. And this is called the sodium layer, and this is roughly 50 or so miles above the Earth. And this is approximately where the Kármán line is. And I'll talk a little bit more about the Kármán line a little bit later off. That's kind of the legal definition of where space starts. It's either 50 miles or 100 kilometers, depending on what country you're in. Those are not the same, by the way. But the idea of the Kármán line is that this is where the atmosphere is thinned out enough. You've gotten far enough away from Earth. Most of the atmosphere is packed under you for that Kármán line. That basically airplanes just don't. Airplanes can't get anywhere near that high anyways, but this is the point where aerodynamic forces are pretty negligible, and you're definitely a spacecraft, and this is where astronauts' wings are given, because you've basically left the atmosphere. There's still technically a little bit more atmosphere left that goes up a good deal higher, where in low Earth orbit you still have to punch away a couple of atoms every now and then. It'll cause your spacecraft to fall in. But this is kind of this is the edge of space kind of thing. And the sodium line happens to be from meteorites burning up in our atmosphere, leaving sodium, that then tends to give off a yellow glow if you excite it, say from heat or from other sources of light and whatnot. The reason I want to point this out is notice how close, when you're zoomed back and you're part way to the moon taking a picture, the atmosphere is a very thin layer. Most of what we think about, most of the life we live, is this very thin layer on the Earth. And the atmosphere is one of the thicker layers, and it's still a very thin layer. 50 miles is a long distance to walk, and it's definitely a long distance to, jump upwards. But in the grand scheme of things, 50 miles across the Earth's surface, that's an hour drive, probably less depending on traffic. I mean, some places, good luck, it's a parking lot, but you get the idea. So we exist, on the scale of the Earth, we exist on a very thin layer, and our atmosphere is fairly thin, and most of what we're going to be talking about in this video doesn't even go up that far. So we've got several layers of the atmosphere, and we're mostly going to be focusing on the bottom layer, the troposphere. But that is for a little bit later on in the video, because before we dive into our atmosphere, I want to talk about how gases work, because, the atmosphere is made of gases. So we need to talk about those a little bit. And this is one of those where me as a chemist goes, oh, wait, I know this. This is a topic that as a chemist, I quite often discuss with my classes. It's usually a dedicated module, because historically, we understood chemistry first by understanding gases. So they have some interesting properties, and they have a lot of assumptions you can start making that they're not perfect, but they're actually pretty good. That simplifies the calculations a lot and allowed us to actually understand them. You can't start with the really complicated stuff. You got to start learning from the simple stuff, both as a person, but also as a society. Okay, so when dealing with this, we can quite often call gases ideal gases. And these are gases that behave close enough to a description that makes a lot of simplifications. So we can make a couple of really big simplifications, and these gases are going to behave close enough to those. And most gases you encounter in an environment that you could survive in are going to be more or less ideal. Now, there will be gases that don't. We usually call those real gases, and there's more complicated math. We're going to just do a quick glance at some of the ideal gas math. We're not going to do any of the complicated math for real gases, because that's well beyond the scope of this video series. Okay, generally speaking, when we understand gases, real or ideal, we use the kinetic molecular theory of gases. So in the kinetic molecular theory of gases, we've got particles and molecules, mostly molecules. You could have atoms, and obviously you could have slightly larger particles, but at that point you're probably no longer a gas. So we're doing mostly molecules here. And they're going to be relatively small, and we're going to pretend quite often that they're hard spheres. This is kind of more ideal things. This is one of our assumptions for an ideal gas. They're just hard spheres. Makes the math a little bit easier, kind of bouncing around. And they're going to be just bouncing around all over the place. Hence the kinetic part. So the molecular part, they're molecules. The kinetic part, they're moving. They're moving a lot. These things are moving a ton. And so as they're bouncing around, we can think of them usually as being described by about 4 properties, at least if they're an ideal gas. Real gases, we have to add more properties because there's things we're ignoring in the ideal gas to make the math a lot easier. And conveniently, once again, most gases, it is good enough. Okay, so if you've got a container of gas, then one of the properties is just how much gas do you have. Now, we're going to more or less assume that all different molecules are equivalent, and that's because we're assuming they don't really stick to each other. Their intermolecular forces are kind of negligible, which, once again, under most circumstances is pretty much close enough. The intermolecular forces don't really do that much as gases. They're bouncing around too awful much. And that their size doesn't really matter. Basically, they're spread out enough, they're bouncing around such a large area, that the size of the atom or molecule or whatever the particle is, probably a molecule, is so small that if it was twice as big, it would still be too small to care about. And so that we don't actually care what the gases are. So we wouldn't want to try and track them by weight or anything like that. We basically just need to track how many do we have, how many atoms are bouncing around in here. And of course, as a chemist, I'm going to use moles. Moles is a great unit for this. The next one is, well, how much are they bouncing around? How fast are they moving? Basically, what's their average kinetic energy? Hey, remember that one? So when we talked about heat, we described one of the simpler models for temperature was average kinetic energy. And this is a case where, you know what? This is great. We can use temperature. This is going to describe how much they're bouncing around. Because, you know, they could be going slowly but really heavy, or they could be going really quick but kind of light. And those will end up kind of canceling themselves out. So we want average kinetic energy. Now, quick point when it comes to units for temperature. We have got a couple of options. First off, we could use something like centigrade or Fahrenheit, but there's a major problem with those, so we really can't use those. Those are what are known as relative scales. Basically, we picked effectively arbitrary. We just picked a temperature to be 0 and then another to be 100, and then we made a scale off of that. So Celsius, it's the freezing and boiling points of water at sea level, and it's going to be pure water in that case. Fahrenheit, we're not entirely sure why these numbers got picked, but it appears to be 100 degrees Fahrenheit is like as high as where Fahrenheit lived. These are all named, Fahrenheit was a person. And then 0 degrees appears to be the freezing point of seawater, maybe. The historians are kind of arguing a bit over exactly why Fahrenheit picked those 0 points. But either way, you've got these zeros that don't actually represent zero kinetic energy. We want something where the kinetic energy is effectively 0. Now, caveat, if we were trying to do a temperature at what we call absolute 0, the definition of temperature kind of breaks down around absolute 0, but we're not really going to be working around there. So we can just start off where absolute 0 would be, where your kinetic energy would be effectively 0. And so we need an absolute scale. So where 0 is 0 kinetic energy. Once again, temperature breaks down if you get too close to it, but we're going to keep a little bit away from that. There are 2 scales to do this, Kelvin and Rankine. Kelvin is basically taking Celsius units and using them, but starting at absolute 0 instead of the freezing point of water. There's 273.15 degrees Celsius between those 2 spots. So to get Kelvin, you take your Celsius, you add 273.15. Once again, they're the same unit. If you do a delta T, so a change in temperature, as long as you're consistent, they're the same, because they're the same unit. Just a different starting point. Fahrenheit has the exact same thing that's called Rankine. This one has fallen out of favor, so not used much, if hardly at all anymore, but it's Fahrenheit units starting at absolute 0. So you're going to be adding 400 and some, I think. The fact that I don't actually know that conversion shows how much that this approach is kind of no longer a thing. But it's always nice to mention Rankine. And by the way, all 4 units are named after people who had big influence in this area of science. Okay, so we've got ourselves moles and Kelvin. Let's be honest, it's Kelvin. So describing amount and temperature. The next 2 are going to be volume. Volume is technically the volume of the container that is empty, so basically the empty space for the gas particles bounce around in. But if it's an ideal gas, we're assuming they're really tiny compared to the size of the container, so that they're not taking up enough of us for us to care about. So the volume is the volume of the container. In an ideal gas, in a real gas, you do have to subtract off the combined volume of all the particles. So if you got a lot of gas crammed in there, well, you're going to have to take into account the size of each of the particles and all of them together. They're going to make a meaningful difference. But, you know, if you're not, then, hey, they're nice and spread out. The last one is pressure. All these particles are bouncing around. They're slamming against the walls, and they're bouncing off of each other. We're assuming they're just going to bounce off nice and elastically. Once again, if they don't, we have to factor that in using one of the real gas formulas. There are a few. But we're going to assume they bounce off nice and, you know, elastically. However, you know, when 2 things bounce off, you know, F equals ma. You're going to transfer your momentum, you're going to change direction, you're going to exert a force. And so that means if you got the sides of the container, all these particles bouncing off of you are going to continually push on that container. And the bigger the container it is, the more they're going to push, or the more often they get hit, the more they're going to push, or the faster they're going, the more they're going to push. And so this push is going to be what we call pressure. Now, there's several different ways of measuring it. So to describe the units, it's really helpful to describe how they're where they come from. The simplest one would be to look at just the force and divide it by the area, because if you had the same gas but it just had more area to push, it's going to push more. So if you're using US customary units, this is going to be pounds per square inch. So basically a target 1 square inch in size and a force in pounds. Pounds, by the way, are both a force unit and a mass unit. They're actually 2 different units, but they're both pounds. Yeah, it's a bit of a mess. But you'd use the force pounds divided by the area of the target in square inches, and you get pounds per square inch, or PSI. Generally speaking, atmosphere at sea level is going to be around 14.7 PSI. Alternatively, if we're using SI system, the SI unit of force is the Newton. The unit of area we're going to use is the square meter. Now, of course, square inch is like, that big, kind of. Square meter is like that big, kind of. So much larger area, and it turns out a Newton is a lot smaller than a pound. So the Newton is a relatively small unit of force, and the square meter is a relatively large unit of area. So atmospheric pressure on average at sea level is going to be around 101,000 newtons per meter squared, which we renamed that the Pascal. So 101,000, I think there's like 101,300 and some odd pascals for just atmospheric pressure at sea level on average. Okay, that's a big number, so we're not going to use pascals quite often. We use kilopascals, just so it's not 101,000, it's 101 kilo, which, same thing. There is an alternative unit which is derived from this. That's the bar. You'll see the bar used a lot. That's 100 kilopascals. It's just slightly less than what normal atmospheric pressure would be at sea. Now, there is a completely different way to measure this, and that is by using effectively a straw. So if you suck up a Slurpee, the Slurpee isn't pulled into your mouth, it's pushed. And so what's going to happen is air pressure, assuming you're in an atmosphere, which if you're not, you're probably not drinking a Slurpee. Air pressure is pushing on the Slurpee and on everything constantly at a relatively constant rate. If you're around sea level, you're dealing with, 14.7 pounds per square inch, which is like a lot. 14.7 pounds, that's like the weight of a dog. Medium small dog, maybe larger cat kind of thing, but you get the idea. That's per square inch. That's a lot. But it's evenly pushing on all parts, so it kind of cancels itself out. Nothing really happens. But what you do is you take the straw, you put it in your Slurpee, and then you're going to suck on it. You're going to use your lungs to lower the pressure in your lungs, in your mouth, in the straw. And remember when we talked about forces and net force, kind of a balance of force. Well, if you're pushing down on the Slurpee with 14.7 pounds, except for in the straw where you're only pushing on the Slurpee with, say, 14 pounds per square inch, well, it's going to go up because you now have this, 0.7 pound per square inch differential. By the way, I'm just making up numbers here. I do not know how hard a human can suck. But the interesting feature on there is because the pressure is in force per square inch, and gravity is pulling on things as well, because we've got gravity going on there. Turns out the area of the straw ends up canceling out, factoring in the pull of gravity, and the bigger the straw is, the more material you're pulling up, but the more area you have for the pressure, the areas manage to cancel themselves out. So this means we can measure the difference in pressure between two sources by how high up you can suck a liquid. That's how a barometer works. You are going to take a sealed tube, fill it with a liquid. In this case, the liquid's going to be mercury. We want something that doesn't want to boil. It needs to be very low volatility. The lower your pressure is, the easier it is for particles to bubble up and escape into the atmosphere and form bubbles on the inside. We don't want that to happen. So we want something with a very low vapor pressure, something that's not going to create a bunch of vapor easily. And also we need something that's got a lot of density so that it doesn't have to be a really tall straw. If this was water, one, it would try and boil, but also it would go up like a couple of stories at least. It's over a story as far as height goes. So we're going to use mercury. And so you take the tube, you fill it with mercury, you turn it upside down. There's no air in the tube, so you create a vacuum in the inside of the tube, and that's going to try and pull the mercury up. and the height the mercury can be pushed up into the tube by the air around it is going to be your air pressure. We describe that typically in millimeters of mercury, although you will also see centimeters of mercury and inches of mercury floating around as well. And so that's another way of describing this one. Alternatively, we'll call this torr. Torr is defined very slightly differently. I do not know enough to know the difference between the two, only that there is an ever so slight difference, even though for all practical purposes, millimeters of mercury and torr are going to be the same number for anything normal people would ever be using it for. There's one last way of doing a unit, and that is discussing a relative unit, irrelevant to some reference, like average sea level pressure. Yeah, there's a reason I was referencing all the other units based on what you would experience at sea level. Partially to give you a general perception of the scale for each one of these units, but also to reference that all of those conversions would equal 1 ATM or 1 atmosphere. Generally speaking, as far as units of pressure go, you see the bar a lot anymore. Chemists, we like ourselves some torr, and of course pascals are the SI unit. Atmospheres you see mostly in more adjacent fields. So a lot of education uses atmospheres, and I do remember seeing that a lot when I was learning to do scuba diving. But then again, I'm only open water certified, so it could just be the entry level scuba diving talks in atmospheres, and everyone switches over to bar, because keep in mind, a bar is pretty close to an atmosphere. This is kind of a slightly scrawny one. Now, there's a couple more properties I want to discuss about gases, other than just kind of the big ones, because this is where things are going to get a little bit more interesting. Okay, so for starters, here is what we call the ideal gas law equation. This has to get a bit more complicated if you're not making the assumptions. There's a couple ways to modify this, but we are going to keep with the assumptions that the particles in the gas aren't sticking to each other and that they're really small compared to the volume of the container that they're in. So we're going to use this guy. So this equation, PV equals nRT, P is pressure, V is volume, N is moles, T is temperature. It has to be an absolute unit. The other units are a little bit more forgiving, but T has to be in Kelvin or Rankine, and no one uses Rankine. R is what's called the gas constant. Basically, it cleans up all the units, and so you have to make sure your units and your R's units all match, and thus you can plug in things. Now, there's a couple of things that this kind of leads us into. Well, let's say I don't have a pure gas. Most of the time, I don't have a pure gas. Most of the time, I have a mixture. Our atmosphere is generally a mixture of gases. You've got a lot of nitrogen, about 70-some-odd% of the atmosphere is nitrogen. About 20-some percent, about 21% is oxygen, and then you've got things like CO2, water vapor, etc. So it's not just the one gas. And this was actually one of the big things in the 18th century that was being discovered by chemists, was like, it's not just air. Air is not air. Air is many things combined. So when we think about an ideal gas, we can plug in all those values in that equation just for the total, all the gases combined, and it works fine. But what if we want to kind of separate things out? You know, if I'm doing combustion, I don't care about the nitrogen. Nitrogen doesn't do anything. I care about the oxygen. So it's pretty obvious I could have, you know, the N total there. So I could have the N and PV equals nRT. That could be my total moles, or it could be the moles of one component of it. And so I could take all the components and add them up and get my total number of moles. That makes sense. But if I'm going to kind of split this apart, then I'm going to have to split at least one of the other properties apart as well. Otherwise, I get a bunch of equations that just don't work. So let's think about the properties we got and which ones maybe we could split apart into, you know, total and then plus each one of the other components. Temperature. That would just be weird because they all have the same relative average kinetic energy going on over here. You know, the oxygen doesn't have a lot of kinetic energy and the nitrogen have a little bit, and then that's how you get the average. They're all bumping into each other. So some are going to be going faster than others, but if you did averages, they're all the same average. So that doesn't make sense. Volume? Okay, that makes a little bit more sense. If I had like all the gas on one side of the container and all the other gas on the other side of the container, what fraction of the container? I mean, that makes sense, but it's not even the least of what's happening. So better than temperature, but no. What about pressure? Here's where something gets a little bit more interesting, and we might be able to add some nuance. So if I'm doing a chemical reaction, that always involves atoms and molecules smacking into each other, and thus doing the reaction. Reaction don't happen if the two atoms don't come in contact with each other. Well, pressure is basically the gas slamming against the wall. So if I've got a wall that's, some fuel, it's a pool of fuel that's going to burn, or a cloud of vapor, little droplets that are going to burn. As the nitrogen slamming into it, it's not going to do anything. But the oxygen, when the oxygen's slamming into it, well, that's a big deal. So we can think about a mixture of gases, and we have the different amounts of each gas, but then we can also break apart the pressure into how much force is being pushed on the sides of the container by one gas, say the nitrogen, and then how much is being pushed on by a different gas, say the oxygen. And that is going to lead us into things like reactivity. The more you get pushed on by the gas that you're reacting with, say the oxygen in fire, the more you're going to do a reaction. So we call this partial pressure, and this gets into Dalton's law of partial pressures. Basically, you can have the total pressure of the gas, and that's the sum of all the partial pressures of all the gases in the mixture. And quite often, we don't care about the total pressure, at least as chemists. Obviously, if we're doing physics, we care about the total pressure quite a bit. But as chemists, we quite often care more about the partial pressure. And a classic example would be mountain climbers. As Earth is pulling on our atmosphere and squishing it in nice and tight, the closer we are to the ground, the more atmosphere we have above us and the more it's squishing it in. So atmospheric pressure is lowest at the ground, and the higher up you go, the lower it gets. We have about 21% oxygen on Earth. So that would mean if we have 1 atmosphere of pressure, then oxygen, we'd have 0.21 atmospheres of oxygen for its partial pressure. Now, if I climb up on a mountain, my lungs, if they were at sea level, they're working great at 0.21 atmospheres of oxygen. But now my total pressure might be noticeably less. Let's say it's 0.5 atmospheres. I'm just making up numbers to make easy math. So if my total pressure is 0.5 atmosphere and 21% of that's oxygen, then I'm just a little bit over 0.1 atmospheres for my partial pressure of the oxygen. My lungs are not going to be working nearly as well as they were at sea level. This may not be enough for me to survive. I don't actually know the specific numbers for how much you can handle, etc. But you get the general idea. I'm definitely going to be feeling it if I'm not in a lot of trouble. Now, when this happens, you might want to supplement some oxygen. So you got 2 choices. You could keep the percentage at 21% oxygen and increase the total pressure. That's how spacesuits work, kind of. Because you're going to need a spacesuit. You got to keep that air trapped next to you, otherwise it's going to leak out. Trying to increase total pressure is really hard. Alternatively, instead of increasing the total pressure, I could increase the percentage of oxygen. Basically inhale more oxygen, less nitrogen. If I go up to 42%, well, that's going to be 42% of half, or 0.21 atmospheres. Yay, I'm back to where I was. And mountain climbers will do this. They will, if they're going on a particularly tall mountain like Everest, they will drag with them oxygen tanks so they can get increased oxygen in their system, which if your mountain's as high as Everest, that's kind of needed. Now, we also see this with things like combustion and fires. If you've got a house where someone's on tanked oxygen, if they've got the machine that sucks the oxygen out of the atmosphere, kind of purifies it and shoves it into a breathing device, that's not going to enrich it. But if you got a big old tank of oxygen with you and you're inhaling it that way, then yeah, that's going to enrich the oxygen in the house. That means any reaction involving oxygen is going to go much faster, which is why there's usually big signs on the house saying, "Do not smoke." The place could burn down really quickly if you've got an enriched oxygen environment. Now, let's jump in to a couple derivatives that we're getting from this idea of partial pressure. One of which is what's known as vapor pressure. So if you have a vapor, this is going to be a liquid that is also a gas at that temperature and pressure. So essentially it's going to be doing equilibrium. You may be predominantly a gas or predominantly a liquid at that particular temperature and pressure, but you're able to do a bit of an equilibrium between the two. Now, if you have plenty of liquid, lots of liquid, then you're going to do an equilibrium such that you're going to load up as much of the vapor over the liquid as can be held at that particular temperature. We call that the vapor pressure, the maximum partial pressure for that liquid at that temperature. But of course, if you don't have enough liquid on hand, you don't have to get up to the maximum. Now, if you've got a big puddle and you're right above it, yeah, you're probably going to be right at the maximum. So we can compare the maximum to how much we actually have, what our actual partial pressure is. And I want to dive into the wonderful world of water here, because this is going to be fairly relevant for us when we're talking about water vapor. One, we got a bunch of water on our planet, and you know what? It's a vapor. It definitely does this whole equilibrium thing. So we can describe the amount of water in the air relative to its maximum vapor pressure with a couple of different ways of doing this. One, vapor pressure is determined by temperature. So the higher your temperature, the higher the vapor pressure is. If you go up high enough, your vapor pressure may exceed the total atmospheric pressure, and you start getting bubbles in your solution. We call that boiling. So one way we can describe how much water vapor is in our atmosphere is to say, well, what is the lowest temperature which could still hold that much? Basically, if you were to cool it down, all of a sudden you would shift the equilibrium and some of the water would have to come out of the atmosphere because it can't have that high of a partial pressure. And so some of the water is going to come out and it's going to condense. It's going to form a dew. We call that the dew point. Basically the minimum temperature where if you try and go below it, you're going to start condensating out the vapor in your gas. Alternatively, we could do a percentage. We could say, well, at this temperature, we can have a certain partial pressure, but we only have, say, half of that actually in our gas. So we could say our percent humidity, if we're dealing with water, our percent humidity is 50%. We're 50% of capacity. That capacity being the vapor pressure, which is determined pretty much solely by the temperature. If you add a bunch of solute in your liquid, then that's a slightly different story, but we're not going to go there. We're dealing reasonably pure water. For what we're doing, even ocean water is close enough. Vapor pressure doesn't change that awful much. It changes a little bit, but not a ton. Okay, so this is one way of looking at it. There's another way we can rearrange the ideal gas law that's going to make things really interesting for us. So let's do a bit of algebra. Yay, everyone wants algebra. So I'm going to rearrange my ideal gas law. So PV equals nRT, and I'm going to rearrange it so that it is P divided by RT equals N over V. Basically, I'm going to move the volume to one side. I'm going to move the RT to the other side. So now I've got P over RT equals N over V. And you are very rightly probably going, yeah, so? Okay, let's add one more term. I'm going to multiply both sides by the formula weight of the gas in question, FW. You're still probably going, okay. Well, think back to when we talked about chemistry. Moles times formula weight is going to give you mass. So that N FW over V is actually going to be mass over volume. Do you remember something that was mass over volume? You got it, density. We've now got this description where pressure times the formula weight divided by the gas constant R times the temperature is going to equal the density. We've got some things we can change, and we can change the density. And this is going to become really important as differences in density are going to be driving our weather. Okay, so functionally, there are basically two terms we have a lot of control over. That's going to be the temperature, and that's the formula weight. Control may be the wrong word, but two terms we want to pay attention to here. Let's talk examples where the temperature is different and where the formula weight might be different. Let's talk temperature. You're all familiar with these good old hot air balloons. So you take a hot air balloon, you take a bunch of air in a big balloon, and you take what's basically a gigantic blowtorch and heat her up, and the air inside the balloon is rather toasty. And now, as the air gets hot, it's going to expand. A lot of the gas is going to be pushed out of the balloon. So, hey, as the temperature goes up, notice it's in the denominator, it's going to cause the density to go down. Remember, when you get a fluid, gas or liquid, the lower density object is going to float in the higher density fluid, and hot air balloons float. This is why. This is actually going to become really important for weather systems because air will also float. However, we could change this up a little bit. We could look at, instead of changing the temperature of the gas, we could change the gas outright. We could do a helium balloon. Helium has a formula weight of around 4 Daltons, whereas air, on average, has a formula weight of around 29-ish. So I fill my balloon not with air, but with helium at the same temperature. Hey, the helium is going to have a much lower mass, it's a lower density, and it's going to float. This is how weather balloons work, and those party balloons. Oh, we can actually go the other way around. Picture on screen, this is known as a mazooka. Translates to evil wind. In volcanic regions of the world, such as the Great Rift Valley, or in this particular example is a volcanic region in California, you have carbon dioxide-rich gas being released from volcanic vents. It doesn't mix with the air very well. It's surprising how little mixing you can get. If you don't have a lot of turbulence, you can get this nice layering, or in this case, this not so nice layering. And so you can get this plume of carbon dioxide that leaks out along the ground, getting trapped underneath snowbanks, in depressions in the ground, in the soil, which can cause tree die-offs, or in things like basements or enclosed containers, such as houses and cabins and tents and whatnot. Carbon dioxide's formula weight is 44. It's heavier than the air. That's why it sinks. It doesn't rise up. Now, if it gets mixed up, that's a slightly different story. But if we don't have a lot of turbulence, we don't have a lot of mixing and stirring going on, it can layer. This, of course, can be a problem. Carbon dioxide is toxic, especially in high concentrations, and these mazookas are going to be odorless, colorless. You can't tell unless you get a big lungful of them, in which case it may very well be too late for you. There are definitely parts of the world where these are a serious hazard and have definitely caused fatalities for both humans and livestock. There are approaches to address this, such as specialized flares that release a smoke that is lighter than CO2 but heavier than air, so it kind of leaves a puddle over it to help detect these mazookas. And of course, you can also have an eruption where you have a massive amount of CO2 that creates a cloud. Those can be quite devastating. There's been a couple of really dark instances of those with fairly high fatality rates. Okay, let's move away from high fatality rates and let's jump in and let's start talking actual weather. Okay, so jumping into our weather, we first want to look just a little bit about our atmosphere and where the energy comes to power our weather from. So if I look at the atmosphere, I'll plop this guy on screen, and I may have briefly plopped him on screen earlier, but now I'm actually going to talk about him. So you got the atmosphere. Earth's gravity is pulling it together, and well, it's thicker on the bottom, and as it peters out further and further into what we would frankly call space, there's still a little bit of air left, so we call that the thermosphere, but let's start from the bottom, not from the top. The bottom, 10 kilometers or so, is what we call the troposphere. This is really where we're going to spend the rest of the video. Almost everything we're going to discuss is going to be in the troposphere, and this is where most of our weather is going to happen. Once you get up above about 10 kilometers, you're getting into the stratosphere. This area we didn't really access until we started having things like jet travel, high altitude balloons. So this is definitely stuff that we really only started to really understand in the 20th century. And what we realized is there was a little bit of things going on. And the reason why we separate the troposphere from the stratosphere is due to this next graph over here. It turns out the temperature varies with height. So in the troposphere, very succinctly, temperature, as you get higher, it gets colder, and it gets a lot colder. This is going to be one of the driving features for our weather. But once you get into the stratosphere, you're going to transition through the topopause, which is basically the point where the temperature stops getting colder and starts getting warmer. You go through the stratosphere, and then as you go up, it gets a little bit warmer. After a while, you're going to hit the stratopause, and now in the mesosphere, it's going to get colder again. It's going to get quite a bit colder. Then it's going to go the other direction at the mesopause in the thermosphere, and at the end of the thermosphere, you're just out in space. Now, back to our original image over here before we jump into an explanation of what's going on with all those temperatures. As we're looking at this one, the troposphere is basically where your weather is going to happen, and this is going to be the focus for the video. Stratosphere, we're going to get some of our high-altitude balloons. Jets are going to be flying at the bottom end of this one. Air's thinner, it's easier for the jets to travel. But it's thin enough you have to compressurize the cabin, or everyone has to wear a gas mask. That's why the little things drop down from the ceiling, because if you're in the stratosphere and things go really wrong, you need to enrich your oxygen because you don't have enough outside air pressure. Otherwise, you're going to suffer severe brain damage just from no air. So you're going to die of lack of air. But if you can get a little bit of oxygen and the pilot can get low fast, then you might not be in a horrible situation. Once again, though, I definitely don't want to be in a situation where I need the little air canisters coming down. Now, you still got a decent amount of air. You can still fly at this point. Once you start getting high up in the stratosphere and into the mesosphere, planes aren't really going to be working to all that much. You're really leaving what we would consider the atmosphere, and the Kármán line is going to be around the mesosphere or low thermosphere, depending on which Kármán line you use, because the US and the rest of the world have two slightly different Kármán lines, either 50 miles or 100 kilometers, which is 62 miles. This is the part where you're going to see in the mesosphere meteors burning up. This is where you get enough air that if you're traveling really quickly, you're going to have significant aerodynamic forces on short time scales. And so you could get, meteors burning up, creating the sodium line, that kind of thing. So this is around where you saw that line on Hello World. Then a little bit higher up in the thermosphere, towards the bottom, you're going to get your aurora. The sun's radiation and the solar wind is going to be interacting, funneled in by our magnetic field. That's going to excite electrons on atoms in the upper atmosphere, once again, probably towards the bottom of the thermosphere, and that's going to be giving off your aurora. High up in the thermosphere, that's low Earth orbit, effectively. That's where you're going to have a lot of your spacecraft. This particular one must be a little bit on the older side. It has the shuttle. Shuttle obviously hasn't flown for a very long time. And then beyond that, you're in the exosphere, which is welcome to space, basically. Okay, so let's jump into a brief commentary on why the temperature is going back and forth, because that's what's distinguishing those regions. As we started doing weather balloons and sounding rockets, trying to figure out what's going on with our atmosphere. Okay, so most of the energy on Earth is going to be coming from the sun. There's a little bit of nuclear decay going on inside of the Earth, creating volcanoes and whatnot, but that's relatively small amount of energy compared to what gets to the Earth via the sun. Now, the atmosphere is basically transparent to visible light. That's how we can see stars and stuff and see people a long distance. That's probably not a coincidence. Having eyes to see in a fluid with a wavelength that you can see in the fluid is kind of useful. So, there's a reason it's called visible. That's what gets through. Higher energy photons, the ultraviolet, the X-ray, those don't travel through air nearly as well. They still go through air, just not as well, especially some of the really high energy ultraviolet, so like your ultraviolet C, does not get very far through the air. Remember back when we talked about mixtures quite a while ago, we had this idea of Beer's law. Absorbance, basically how much light doesn't get through, expressed as a logarithmic function. equals the concentration of whatever your chromophore is. In this case, it's going to be like oxygen atoms, etc., times the extinction coefficient, basically how good they are at absorbing that one particular light. And then the path length, how far you have to go. So for visible light, the extinction coefficient is just really, really tiny. The air is not really going to stop visible light particularly well. It's quite transparent. But if you go into the ultraviolet or you go into the infrared, that extinction coefficient is actually getting a little bit higher. Different gases in the atmosphere have the ability to absorb light in the ultraviolet or the infrared, and then a bit beyond. So it's not going to just stop at like a brick wall. Remember, your absorbance kind of, peters off. It gets darker and darker the longer you go. But the energy from those photons also don't just go nowhere. They don't just go away. It usually gets turned into heat. So if you got the sun shining, the visible light's basically going to reach the ground, and so you're going to heat up the ground very nicely. Ultraviolet, infrared, those are going to, some of it will get to the ground, but a lot of it will be absorbed by the atmosphere or will be reflected off, so things can bounce. Clouds do a great job of reflecting light, nice, white, and fluffy. We call that albedo, a nice, white, fluffy thing. It doesn't have to be fluffy, but nice and shiny. It's going to reflect a lot of light off. If it's really dark, it's going to absorb a lot of light. Clouds are very light, so they tend to reflect a fair amount, although they do it in both directions. Clouds at night, however, will bounce the light up if it's trying to radiate off the Earth. Okay, so now we're heating up the atmosphere, we're heating up the ground. Due to black body radiation, the hotter you are, the higher energy photons you get, but you're not that hot. So most of the photons being released are going to be released in the form of infrared. Now, some of those are just going to go straight back off into space. Keep in mind, we're in, Earth is floating around in outer space. Outer space, the only way you can transfer heat is with radiation. There is no substance in order to do conduction or convection in outer space. So we've got to get everything down to radiation. So the ground can radiate off heat in the form of infrared. Some of that is going to get absorbed by the atmosphere. A little bit's going to go straight off into space, but some of that's going to be absorbed by the atmosphere relatively low to the ground, and it's going to get warmed up. Likewise, clouds might bounce it back down. Now, as the air close to the ground warms up, it's going to start emitting infrared radiation. Now, it's going to go back down towards the ground, but it's also going to go up towards the next layer of air. And that's going to start warming up. But it's also getting warmed up by the sun because the sun is also giving off infrared, and it's warming up as we go down. And so now you've got this heat getting these layers of equilibrium as you go up further and further into the atmosphere. And this is one of the reasons why we're getting the temperatures going back and forth. So you get this flow of heat coming down from the sun, but also coming back up from the Earth and reaching their own equilibriums. Obviously, I've skipped convection so far. I'm going to get to convection because it's going to be a really big deal. But we get this idea of layering for your atmosphere. Now, this means, though, that effectively, when it comes to convection, the atmosphere, at least on the lower part, the troposphere, that is going to be heated pretty much from below. So you're going to be heating that up from the water and from the land, whatever's on the surface. And so now we get a situation where we can get ourselves some convection going on, and we get some nice little convection currents. One of these can be pretty easily seen on a coastal situation where you get diurnal wind change. Diurnal basically means day to day, or day versus night. This is kind of the best way of describing it. So if you're out in a place like San Diego, San Diego's pretty pronounced here. You've got a bunch of land. Now, land has a relatively low specific heat. So during the day, the radiation is coming, it's heating the water, it's heating the land. Water has a very high specific heat. Land has a relatively low specific heat, especially if it's relatively dry. San Diego is kind of dry. Absolutely gorgeous, but kind of on the dry side. You got a lot of deserts out in the American Southwest. So as the sun heats the land gets hot. That energy is conveyed into the air above it by all of the methods. and that air gets warm. As the air gets warm, it starts to expand, its density lowers. Now, if we look over the air over the ocean, it's also getting warmer, but it's not getting as warm. The ocean's taking a lot of energy in order to heat that up. So the air over the ocean, it's not expanding as much. Its density is higher, and it's going to displace the warm air over the land. And so you get this breeze from the ocean. It's going to be this cool breeze. Now, as the day transitions to night, the land is going to cool off quick. Remember, its specific heat's relatively low, so the land cools off quick, and the air above the land is going to start cooling off. The ocean, however, does not cool off as much. It's got a very high specific heat. It stored a lot of thermal energy in the ocean, so it's going to still heat up the air. So now the story is going to be reversed. The air over the land is going to be cooler than the air of the ocean. The ocean is still going to be relatively expanded. The air of the land is going to be somewhat contracted, and so it's going to have a higher density, and so it's going to push out the air over the ocean, and that's going to cause that to rise. So you're going to have a breeze at night going off into the ocean. So your breeze is going to switch day versus night. This is one of the reasons why the weather is so beautiful in San Diego. You're in the middle of a desert, it's nice and sunny, but it's not as hot as you expect because you get the cool breeze from the ocean to cool you off, and then it stays warmer during the night. So you don't get quite the swing that you would, say, over in Yuma, which is a couple hours away from San Diego. Completely not surrounded by oceans, quite the opposite. Okay, so we've got this idea where we can start getting convection currents. But we can also start thinking of a couple other scenarios. Remember, the higher up you go, the colder you're going to get. And here's where I want to start bringing in the wonderful world of moisture. So if you're over an ocean or a large wet environment and you're fairly warm, you can start evaporating water. It's going to start becoming a vapor, and you can increase your humidity. You get nice, warm, moist air. Now, we can take things in a slightly different direction. If you've got a prevailing wind going on, and I'll get to why we get prevailing winds here in a minute, but if you've got a prevailing wind and it's pushing the air along, but instead of just nice flat area where it can just kind of float along nicely, it's going to go hit some mountains. Think somewhere such as the Pacific Northwest, up Oregon, Washington, etc. So as you're going up a mountain, you got these nice, warm, moist air, and it's going up a mountain. The mountain's causing it to rise up. Remember, your temperature starts going down as you go up in altitude, at least within the troposphere, which we're not really going to hit stratosphere. So temperature goes down as you go up, at least as high as we're going to go. So now the air is going up higher, and it's going to start cooling off. So remember when we talked about vapor pressure is controlled by temperature. Well, if the vapor pressure goes below what it actually is, so if it cools off too much and your maximum is less than what you got, well, that water can't stay in the atmosphere. It's got to precipitate out. And so you're going to start getting a lot of rain. So the water is going to start forming raindrops. Generally speaking, it needs a small nucleation site, so a bit of dust or sand or pollen or whatnot for the water to clump around. Then it can form a raindrop and fall down, and you get nice showers. It's going to be on the windward side of the mountain. Now, once the air crosses the mountain, goes over the mountain, now it's on the leeward side, so the back side of the mountain. Well, it's already gotten rid of a lot of the water, so it's very dry air. This is going to create what we call a rain shadow. So if you look at the Rockies, they go up and down the United States. Most of the United States is kind of leeward of the Rockies, definitely the Great Plains, a lot of the Southwest, Yuma, like I mentioned earlier. So this is going to dry things out quite a bit. And so you have a fairly dry environment. We don't think of the Great Plains as a desert, but it is actually a relatively low moisture environment. You do get a fair amount of water there, but not nearly as much as you might want to expect. So you get some relatively low moisture environments up into the middle of the United States and Canada due to the Rocky Mountains. And of course, you just squeezed out all of this water. It had to go somewhere. So if you're on the windward side of the mountain, say Oregon or parts of Oregon, Washington, etc., you get lots of water, and therefore you can have a temperate rainforest in that particular case. Now, by the way, when I'm talking about rain, I do want to make a quick point. Raindrops are not teardrops. Teardrops are water dripping from a source. It's held on to, your face kind of thing as it's going. If the water's floating free, you've got air pushing it up, so they kind of look like hamburger buns, not really like teardrops. Also, if they get too big, they split apart into smaller droplets. Okay, now remember in the heat video when I said this about convection. I should point out that convection currents usually aren't one big giant circle. Quite often we draw them as one big giant circle, and sometimes they can be one big giant circle, but quite often we get little pockets where you get these individual circulating cells. This is going to be important for weather, because weather is going to be heavily involved by these pockets of circulating cells, as well as things like ocean currents, the picture you can't see behind my head. Yeah, that's going to become important for us. The convection on Earth, as we've got the sun warming the land and the water, it's heating from below, the warm air is rising, or it's the cold air sinking, shoving the warm air out of the way because the gravity is pulling on the cold air a little bit more because it's denser and therefore it's trying to get down, or it's pulling it down. You don't get one nice clean cycle. Instead, you get a bunch of kind of cells. And so we can look at a picture of the Earth and we get these cells of convection that, generally speaking, are separated every roughly 30 degrees of latitude. And so this gives us a series of cells going on. Now these are going to fluctuate a bit as time goes on, and this is also going to start getting some currents of air flowing because the Earth is spinning, and of course the Earth is spinning underneath the air, and as the air is convecting, you get some rotational effort going on, and so you're going to get some interesting patterns of winds. So some of your windwards direction are going one way, some are going to be going the other way. So this is going to create some side to side. But you also have areas where the air is going up. Where your air is going up, it's rising, you're going to have a low pressure area going on in that area. And where the air is coming down, the cool air is coming down and dropping, that's going to create a bit of a high pressure area because you're actually being pounded by the air flowing on top of you. So you got the cold, dry air coming down. It's going to be warming up on its way down. But there's not a lot of water going on here. The high pressure systems are going to bring generally clear skies. So nice sunny environment. Low pressure systems, very much the opposite. You've got warm air, probably warm moist air, and it's going to be going up. Now the more moisture you got in there, as you go up, the temperature is going to be dropping. Same story that happened on that mountain, but we're potentially going much higher. So that water is going to have to come out in the form of some form of precipitation. Now, depending on how high up it gets, there's a very good chance it's actually going to freeze into some form of ice. And so as it's fairly high up, it freezes into ice. Now, if there's a lot of wind pushing it, the ice can stay aloft and stay in the clouds. This is why we're getting clouds. We're condensing our water, we're turning it into droplets, potentially ice crystals within the clouds, and they're being kept aloft by the water pushing up. As you notice, my hands keep going like this, even though you can't see them on camera. But if the ice crystals get too big or the water droplets get too big, they're going to come down. And so you're going to get precipitation. Now, as you're doing this, if they're going through an area of warm air, quite often we're going to see different air masses interacting, and I'm going to pull up a picture of the United States here and start talking about different air masses interacting. But if you've got a nice warm air mass, then if you've got ice crystals up top, they're going to melt and you're going to get rain. If you don't, they're going to come straight down, you're going to get snow. If you've got some warm air, but not a lot, then if you've got just a little, you're going to get some sleet. If you've got a medium amount, you're going to get freezing rain. Basically, they melted, but they're almost freezing. By the time they hit the ground, they're going to be frozen. So depending on your environment around you. Now, if you've got really strong winds, they might be going up and down, up and down, up and down, and this is how you build hail. By precipitating down, you've got your ice, it starts to melt. maybe grabs a few water droplets on the way down as it runs into it, then winds blow it back up to where it refreezes, and then goes down and back up and down and back up. And instead of having little things, you get balls of ice that keep getting bigger and bigger and bigger. They can break things once they finally hit the ground. So let's talk a bit more about where those storms are coming from, because you've got a few options. Basically, we need warm, moist air to go up. And so as it cools off, it can't hold the water. So a few scenarios can do this. One, you can have a low pressure area where the air is convecting upwards. That's going to do this. We especially see this quite often at, say, the equator, where you get lots of rain because that happens to be an area of low pressure. Rain goes up. It was already very warm, very moist, and it's going to cool off quite a bit as it's coming down. Or you could have the windward side of a mountain where it's going up the mountain, and thus it's going to go off. But you can also run into, say, mountains in the air. I'm being way too poetic on that one. You can have air masses. So I'm going to pop up a map of the United States. This is just kind of an example map of what we usually see. And this is lower 48. I'm going to be a little bit US-centric on this discussion. But jumping in on this one, quite often you're going to get a bunch of different air masses. Now in the US, we kind of commonly see about 3 major air masses. We've got cold, dry air coming in from the north and west. Farther north you go, generally things are a little bit on the cooler side. And that's going to be blown in towards the United States, depending on the weather exactly. We pay meteorologists for a reason to sort this out, to know exactly what's going to go when. The American Southwest, we've got a fairly decent amount of warm, dry air that's going to be blowing more towards the east. And then we're going to have warm, moist air blowing up from the Gulf of Mexico. We get a lot of our water in the United States from the Gulf of Mexico. We actually have a couple different sources of water. But for a lot of us, a lot of the moisture we get, especially over on the East Coast, is coming up from the Gulf of Mexico. So we have 3 air masses, and they're kind of moving around. So as they're moving around, they're going to bump into each other. And when they bump into each other, you're going to get a front. And it depends on which 2 are bumping into each other, or which ones are bumping into each other, are going to get you your front. So if you've got the warm, moist air bumping into the cold, dry air, the warm, moist air is lower density, and so it's going to kind of go up. And so as it's going up, it's going to cool off. You're going to get clouds and potentially some precipitation, usually nothing too awful violent. There's a way of describing kind of the energy involved in a system, CAPE, or conductive available potential energy. So you have potential energy by this ability to go up, or more accurately, I would say the cold, dry air, the ability to go down kind of thing. And so you don't have too much CAPE going on over here. The warm air is going to go over the cold air, kind of drag this out, not too big of a deal. Now, if you got the cold air coming into the warm air, well, in this case, the cold air is going to kind of plow in a little bit more aggressively here. It's going to be pushing itself under the warm air and pushing the warm air up. And typically you're going to have a much higher CAPE, a much higher potential energy going on here. And the air is going to be pushing itself up, and you're going to get much more aggressive storms. If you want particularly violent storms, we can come with an inversion. So an inversion is where you get a layer of warm air between your cool air. So instead of going from warm to cool as we go up, we instead go from cool to warm and back to cool. So now, as the air tries to rise, it's not going to rise past that warm air, which is going to trap things like pollutants down low. But also, if that inversion breaks, you can build up quite a bit of potential energy for being able to do convection. So your cap can go up quite a bit. And thus you can get really intense, really violent storms where this particularly breaks, and thus getting a fairly aggressive weather system. Now, let's look at this over here. So if we're back to the map, we've got the warm, moist air going into the cool, dry air. That's your warm front. It's described by a line with that's usually red with little bulges on it, so kind of half circles on it. Then you've got your cold front. That's going to be a blue line with triangles on it. And that's going to be the cold air going into the warm air. Now, where you have the warm, dry air meeting the warm, moist air, this is an area where we call this a dry line. And this is an area where the warm, dry air is actually denser than the cool, moist air. Because keep in mind, water's formula weight is less than that of oxygen and nitrogen. So the more water you put in the air, you actually lower the average formula weight of the gas in the air, and therefore you're going to lower the density. So the warm, dry air is going to push under the warm, moist air, and you get yourself the dry line, which is usually kind of a brown dashed line. Where these meet, where you get the intersection specifically on the dry line, you're going to get a lot of violent storms. Quite often you're going to get a bit of a spin going on, in which case you can run into things like tornadoes and get very aggressive thunderstorms that way. And generally, if we look at US geography, the tornado alley, which is actually starting to shift a bit, but tornado alley is roughly where these three air masses tend to all collide together, thereby giving you some of your more intense storms. It does change depending on the season of the year, and you can get tornadoes outside of Tornado Alley. Canada does occasionally get a tornado. It's rare, but they do have them. So you can kind of get them quite a few different places. But the US is particularly known for our tornadoes because we have these three air masses that very routinely just smash into each other. And it's usually that intersection of those points where we see that interactions. So with that said, have a wonderful day, and I will see you in future videos.